In the last lectures, we have concluded our discussion about a polynomial time algorithm, Edmonds' algorithm for non-bipartite matchings, for finding perfect matchings and matchings in a general graph. And the crux of it was contracting odd cycles. Odd cycles are really kind of the key. In the next series of lectures, we're going to now look at the polyhedral aspects of it and come up with a characterization of the matching polytope and the perfect matching polytope. We're actually going to do those in reverse order. We're going to talk about the perfect matching polytope and then use that to give a polyhedral characterization of the matching polytope. So again, what are we talking about here? We've got a graph, G equals VE, as always, not necessarily bipartite. The two polytopes that we care about, we can easily specify, as with any combinatorial problem, as a convex hull of the incidence vectors of their solution, or the indicator vectors of their solution. So in other words, the PPM stands for the perfect matching polytope, is just by definition the convex hull of the indicator variables x chi m. Again, this is an element of R to the E, where M is a perfect matching. And if your graph is something like a triangle, which fails to have a perfect matching, then this polytope is empty. And then similarly, the matching polytope is the convex hull of the same thing, where now M is just a matching. So it's chi M. It's not even maximal. I'm not even assuming that they're maximal or maximum, such that M is a matching. So in particular, 0 is an element of PM, the matching polytope. So what did we see for bipartite? The matching polytope, the key was these constraints x delta of v less than or equal to 1 was enough to characterize the matching polytope. And then if we put equality, this characterized the perfect matching polytope. But that's not enough in this case. And you can see that a graph like this, where I put weight 1/2 on all the edges, looks like it would be feasible for perfect matching. Whereas we know that, in fact, the perfect matching polytope is empty, is the empty set for the triangle graph, since the triangle graph does not have a perfect matching. And this is completely consistent with the last few lectures that developed an algorithmic solution for matching and perfect matching, because the culprit there, what blocked us from the easy solution of finding augmenting paths, was odd cycles. There's the whole point about contracting blossoms. And again, here we see that if you have, it doesn't have to be a triangle, any odd cycle, if I put halves all the way around, it satisfies basically this constraint, but clearly we have a problem. So we need to deal with odd subsets, odd cycles, but more generally just odd subsets. So let's talk about these constraints. We'll see that the constraint that we really need, that to rule out something like this, 1/2, 1/2, 1/2, intuitively, what do we know that any matching has to satisfy in any odd cycle, or in any odd subset of? You can only take, in this case, 1 out of 3. Or if we have the pentagon, we can only take 2 out of 5. What is that number? It's equal to rounding down 1/2 of the cardinality. So we're going to put, so that simple idea says we know that a perfect matching or a matching has to satisfy those constraints. So let's add them and see what happens. And so again, a lot of the spirit of where these results came from was thinking about additional constraints that a matching must satisfy, or whatever your combinatorial object is, must satisfy, looking at an example that violates it, and then trying to add those back, and then trying once again to see if we satisfy integrality with the suite of tools that we have at our disposal. Primal dual algorithms, specialized methods, polyhedral characterizations, like TDI, TUM, etc. Okay, so let's write these constraints down. I'll explain this notation in a moment. This is the floor of 1/2 cardinality of U for every U subset of V where the cardinality of U is odd. And what this means, this is the set of edges in the subgraph defined by the nodes in U. And so immediately you can see that the triangle violates this, because for U, the triangle graph, x of E of U is equal to the weight on every single edge. So it's 1/2 plus 1/2 plus 1/2, which is 3/2, which is bigger than, rounded down, 1/2 of 3, which is 1. And so that should make us happy. So this is going to rule out the triangle. Okay, so the key result that we're going to prove actually in the next lecture is that this is all we need as far as additional constraints go. So in other words, if we keep our constraints that this is less than or equal to 1 for every node V, and x is non-negative, and now we put these odd subset constraints, x of E of U less than or equal to floor of 1/2 cardinality U. Whoops, I'm a bit sloppy in how I wrote floor. For every U that's odd, let me call this, use similar notation that we've used in the past. Q, the theorem says that for Q defined in this way, Q is equal to, matching. QM is equal to the polytope of matchings. And this, like most of the results on matching, or many of the first and important results on matching, this is a theorem due to Edmonds. We're going to prove this theorem in the next lecture using a characterization of the perfect matching polytope. So the perfect matching polytope is the following. QPM is equal to x non-negative, x of delta of V equals 1, and x of E of U less than or equal to the floor of 1/2 cardinality of U, where U is odd. So this is exactly the same as what we had before, except I just put equality here. So this is natural, that this is what we should expect. Okay, so this turns out is the perfect matching polytope, but we are not going to work with this. What we're actually going to show is integral is another polytope, and once we show integrality of that, it will let me write this down. It will be clear what I'm saying. So instead of working with QP QPM. Let me put a dash, just because we're going to shelve this for a while. Instead of working with QPM, we show that a different characterization, QPM without a dash, which is x non-negative. Again, x of delta of v equals 1. Remember, equals 1 is saying that for every node, it has to be covered by one edge. That's what this is saying, or in sum one edge, but if you have integrality, those results are saying one edge. For non-perfect matching, for just matching, it's less than or equals to 1 because it's saying for any node, you can have at most one edge in the matching incident, but you're allowed to have none if you're allowed to have exposed, if you must have exposed vertices. Okay, now here is I'm going to replace this odd subset constraint with something different, which is related, of course, to, it has to be related to odd cycles. And it is this. For any u that's odd. Okay, so what this is saying, this is the sum of the weights that we assign to edges of all of the edges that have one endpoint in U and one endpoint outside of U. This is our standard notation, our standard cut notation. And again, this is a non-directed graph. So we don't need delta plus and delta minus as we used when we were talking about directed paths. So here's what we're going to prove. We're going to prove that QPM equals the perfect matching polytope. And again, this is due to Edmonds. And then in the next lecture, we're going to show that we're going to use this to show that QM, given on the previous slide, is equal to PM. But once we've shown that, then this will immediately imply that Q dash of PM is equal to the perfect matching polytope, which then therefore justifies us in using this other description. So this is what we're gonna see. Of course, this is going to be the main part of it. This is just kind of a simple corollary of the fact that the QM is equal to PM. Okay, so this is where we are. As a preliminary to the proof, or really this is the first step of the proof, we can even start it here. Note that the fact that the perfect matching polytope is a subset of Q is basically immediate. So again, why is that true? Certainly the perfect matching polytope satisfies non-negativity, and also so in other words, I'm taking any chi m where m is a perfect matching and observing that certainly it's non-negative, certainly it satisfies this property because for every node that node is indeed covered by the matching. And now what does this say? It says that if you have any odd subset of nodes, there must be an edge that goes from outside that set to in the set. And again, this is obvious for perfect matchings because you cannot have some odd, if we have some odd subset of nodes, let me even take away the edges. We're not talking about what the edges are. Here's some odd subset of nodes here. The perfect matching, what this constraint here is saying is that there's got to be an edge connecting to one of the nodes in there in the matching. And again, that's obvious because if you have an odd set of nodes, you can't possibly have all of them be covered, be non-exposed, just by edges joining them. So it's very simple and natural, and it turns out that this is sufficient. So this is this relationship here, this containment is clear. We're going to work with the other containment, which means, as we've done in all the proofs, we basically are going to start with a point in Q and try to show that it must also be in P. So this is our story. Okay, so let's get to this. So let's suppose, for a purpose of a counterexample, that this is sorry, wrong direction. That this is not the case. So suppose that this is not the case. So well, that means that there exists some x in QPM that is a vertex, because we're dealing with polytopes. If one polytope is not contained in another, there must be a vertex of that polytope that's not contained in the other. So there exists some x in QPM that is a vertex of Q that is not in our perfect matching polytope. This is essentially another way to think about a proof by induction, but we're going to so I kind of jumped into this proof a little bit too quickly. What we're saying here is that if this theorem is not true, there exists some graph for which the resulting QPM has a vertex that is not in P. So I'm going to take the smallest such graph. So clearly this is QPM is equal to PPM for many graphs. For example, the graph on one single node or two nodes. So that much is clear. So there exists some such graph. So let me add that in. So let me let G be the smallest graph, i.e. the graph minimizing number of nodes plus number of edges in the graph that exhibits above counterexample. Okay, so now G is the smallest such graph, and this is going to allow me to make conclusions, because this is going to allow me to move forward, because in particular any subgraph where I've removed an edge or I've removed a vertex is not able to exhibit the above. Okay, so what does this immediately tell us? So now back to our vertex, back to our vertex X that is in Q but not in P. What do we know about this vertex? Well, first, note that I claim that X has to have this property. Every coordinate of it has to be strictly positive and has to be strictly less than 1. So why is this? So otherwise, we contradict minimality. Of the graph G, because we could delete an edge if xe equals 0, or a vertex potentially if xe equals 1. So you see, if you have an x that assigns no weight on a particular edge, then if I again looked at the same graph, but except with one edge removed, then again I would have some x that satisfies all of the constraints in QPM, but by assumption is not in PPM. So what does that tell us? If this is the case, then it means this can only happen in what kind of graph? How is it possible that we satisfy all the constraints, yet we also have every xe? One thing that cannot possibly happen is our graph could not look like this for, something like, I don't care about the triangle at this point. What I care about is this node that has degree 1. We cannot have no degree 1 nodes. And so it means that the degree of v is greater than or equal to 2 for every v in v. Otherwise, it doesn't satisfy, where is it? It does not satisfy this. We couldn't possibly satisfy this constraint. We would have to have xe for that single edge incident to v to be equal to 1, and we don't have that. So it means that we have this, and also it means, therefore, that the number of edges is greater than or equal to the number of vertices. And in particular, we know that it's going to be actually strictly greater than, because if the number of edges is equal to the number of vertices, what does that mean? Think about what kind of graphs have that property. Well, it's only going to be a graph that has a cycle. So it has to be. We can't have any situation like this. Here I have 3 edges and 4 vertices. So if E is equal to V, then this means that not only is that it means that each node has degree exactly equal to 2, just by a counting argument. And also, if I have a cycle, it has to be even. Why does it have to be even? It has to be even because of this constraint right here. You see that this is saying that any odd subset has to have an edge coming into it from somewhere outside. And if I have an odd cycle, then it doesn't satisfy. Then it doesn't satisfy this. So it means also all cycles are even length. Because indeed, if I take any for an even cycle, if I take any odd subset, then it does satisfy this. There's at least one edge coming into those 3 nodes from the outside. So then I'll leave this as an exercise for you. If this is the case, then this violates the assumption that x is an extreme point. X is not, contrary to assumption, an extreme point, and that would be a contradiction. So what is the remaining case that we have? Well, that means that thus we have left to consider the case where the degree of v is greater than or equal to 2 for every v in v, as before, but also, and the number of edges is strictly greater than v. Here is where our polyhedral thinking is going to start kicking in, and our characterization of extreme points. So again, think about what this means. If the number of edges in the graph, we're not talking about the support. We know that x is non-zero everywhere. So so E is the number of edges of the graph. Now, if x is a vertex, back to the first lectures in this class, when we were talking about polytopes and characterization of extreme points, we know that there have to be, that whatever dimension it is in, which is E, there have to be that many tight constraints. So if X is a vertex, it means it satisfies E tight constraints. The wording here, what I mean is at least E of the constraints that it has are satisfied with equality. And in particular, there must be E independent constraints that are satisfied with equality. So what are our options? Let me flip back to show you again our polytope. We've got non-negativity constraints. None of those are satisfied with equality. We have a bunch of equality constraints here. So that gives us V equality constraints. And all of those are independent. I'll leave that for you to check, but it's straightforward. So what this tells us is that there has to be at least one of these odd subset constraints which is binding. So let me write that down here. So where are our E tight constraints? We have these constraints, and none are tight by our assumption that X is strictly positive, which again we got from minimality of the graph. Again, this is another way to approach an induction theorem. If we were strictly doing it by induction, we would have observed that for one node, this result clearly follows, and then we would have taken a vertex X and observed that if it doesn't have support on a particular edge, we could just reduce and then use the inductive hypothesis on the subgraph that has that edge missing. So this is really just a proof by induction what we're doing. Okay, so none are tight here. We have the constraints X of delta V equals 1. We have equality because we're talking about perfect matching. This gives V tight and independent constraints. And so we need at least one more. So this means that there exists U. And note that U has to have at least 3 edges. Sorry, has to have at least 3 nodes. Let me write this down. There exists U with U odd and U has at least 3 edges, so it's not one edge. That's obvious because then it just coincides with one of the X of delta V equals 1 constraints. We need independent constraints. And for the same reason of independence, it can't be all but one of the nodes of V. So you can check that if U were the entire graph except for one node, then the resulting tight constraint that we got there would not be independent of all of these single node constraints. So there has to exist U that's odd cardinality. Its cardinality is between 3 and V minus 3. That satisfies this constraint with equality. Okay, so this is what we know so far. And we're going to rely on this odd cycle that we have found. Okay, so now we're going to make 2 new graphs. One is with U contracted. So the concept of contracting this odd set, we haven't said it's a cycle, but contracting an odd set was important for the algorithm, for Edmonds' algorithm, but it's also important for this polyhedral characterization. G prime, let me move this up here, G prime, or G dash, is G with U contracted, and G double dash is G with the complement. I'm going to use bar to denote the complement of U contracted. again, G U and G bar U are created by contracting nodes in U or U bar respectively to a single node, but I'm going to keep all of the edges because I want to keep a correspondence between all of the edges that were not contracted and the rest of the graph. And keeping all of the edges. So what I mean is, if I have something like this, and this is U, remember that we're not U doesn't have to be a cycle or anything at this point. It doesn't have to be a blossom. Then the resulting graph is going to have my supernode here, but I'm going to keep all three edges going in and going out. Okay, very good. So now with this process, my vertex X naturally defines, or naturally corresponds to, X prime or X dash and X double dash just by deleting internal edges. So let me draw some internal edges here of a different color. So this was my original graph. So you can see that in this process, all of the edges joining nodes in U is collapsed, or for G double dash, the nodes in U complement, those go away. I basically just delete those, remove those edges, remove those coordinates from X, and I get either X prime, X dash, or X double dash. So X naturally defines X dash and X double dash. This is essentially by orthogonal projection. By removing coefficients corresponding to internal edges. I hope that's clear. Internal to U or internal to U complement. This is a coordinate projection. All right. So what do we have for X dash and X double dash? So we've got. Do we have X dash non-negative? Certainly. We must have this. Do we have, so all right, check, we have that. Do we have X dash of delta of V equal 1 for every V in G dash? Well, so certainly for anything that wasn't collapsed, we didn't change anything. So that's certainly true. So we only need to worry about, if this is G, this is G dash, I only need to worry about the node that was collapsed. And what guarantees me that I have that? Well, you should think about this just for a second. I'll tell you the answer. But why do we have this? Again, for any node that's not the collapsed node, it's obvious. And for U, why is it obvious? It's obvious exactly because we chose U because it was a tight constraint. U is not just any odd cycle. It is tight. So again, this is true because X of delta of U is equal to 1 by our assumption. In other words, by how we found U. And then all of the other constraints, X dash of delta of U dash greater than or equal to 1 for any U dash subset of V dash of odd cardinality. This follows this is inherited essentially. So check. It also holds because it is inherited from X and G. Because we did not change the parity of any subset. So again, what are we saying here? Let me draw a few other nodes. So suppose we're interested in this odd subset. Okay, it contains, clearly if the odd subset does not contain the collapsed node, then it's that same constraint existed in the uncollapsed graph, so it holds here. So it's only interesting to check this constraint for a subset that contains that collapsed node. And this subset has odd length. And the observation is that because the collapsed node had an odd number of nodes itself, 3 in this case, then in the uncollapsed graph, this thing that I've circled here had 7 nodes. So it was also odd length. And the constraint in the original graph said that all nodes, said that there must be at least one edge, or total weight equaling 1, of all of the edges coming in. And this is why we keep potentially the multi-edges here, because I want to inherit this property. Whatever edges I had before coming in are wherever it is they were going, whether they're going to the special node, to the collapsed node or not, every single one of those is preserved. Only internal edges are the ones that go away, and those internal edges never contributed to satisfying this inequality. So in short, what this tells us is that now we can use our inductive hypothesis. So what does this imply? It implies that X prime satisfies all of the constraints to be an element of Q dash PM, and you can make a similar conclusion for X dash dash. So similarly for X dash dash, so it's in double dash of QPM. But by our inductive assumption, in other words, by assumed minimality of G, G dash and G dash dash are smaller, so it must be that these are perfect matchings. And now you can probably taste the end. It's close, but we still have a little bit of work to do. So how we need to think about how we're going to use these perfect matchings, and how we're going to use those to show that actually X, which we assumed was not in the perfect matching polytope, in fact is. Okay, so X is rational because our original polytope is rational. So of course, this means that X dash and X dash dash are rational. And that means that since those are in the convex hull, that convex hull itself, I can take all of those weights to be rational, which means that I can clear denominators. And that means that a multiple of X dash is equal to a sum of incidence vectors corresponding to perfect matchings, where they're weighted integral by some integral. And so by repeating matchings if necessary, perfect matchings, if necessary, I can write the following. We can say that there exists potentially, by repeating I mean these are not necessarily unique. There exists M1 dash, M2 dash, up to mk dash, not necessarily unique, that are perfect matchings in G dash, which is G with U contracted. I should say something about notation, that this contraction is, something special that we're defining for this proof. I know that in the previous lecture I spent some time talking about contraction being essentially an equivalence relation, and so I used a different type of so I talked about what this means, but here I want to make clear that we're defining this particular contraction and keeping all of the multi-edges for this proof to work. And there exists similarly M1 dash, M2 double dash, MK double dash, same K, that are perfect matchings in G double dash, which is G with U bar contracted, such that X dash is equal to the average of these. Mi dash and X double dash is equal to 1 over K. So, just convince yourself that this is the case, and convince yourself that I can take the same K in both. Okay, so potentially by allowing myself to repeat matchings as necessary. Okay, so this is the consequence of having shown that X dash and X double dash are in Q PM for a smaller graph, Q dash and Q double dash PM, that they're in PPM, and therefore I can write them in this way. Okay, so here's a key point. So now recall that we did not delete edges in the contraction. So recall that edges that were going into U from outside, so edges in this set were not deleted when forming G dash, and similarly when forming G double dash. So similarly for G double dash. So that means that for any edge, any one of these edges that wasn't deleted, we know that just looking at these two boxed equations, this tells me that K times X dash of E, in other words, the coefficient of X dash at that particular edge that's going into U, has to be equal to K times X of E, just because I didn't delete it, but it's also equal to K K of X double dash of E. So what does that tell us? So looking at this set of equations telling us that K of X dash of E equals K of X double dash of E, and again looking at this two equations in star, what is K times X dash of E? It is just counting the number of perfect matchings Mi dash that have E in it. And similarly, K times X double dash of E is just counting the number of matchings M double dash of I, M double dash I, that contain that that edge that we didn't delete. So that means that for any such edge, I'll write it again, for any edge, the number of matchings in G dash and the number with that contain E is the same as the number of matchings in G double dash that contain E. So the number of perfect matchings mi dash with E belonging to them equals the number of matchings mi double dash that have that edge with E. Now, how many edges of that go into U does a matching have? So here's my subset, my odd subset U. So I guess again, it doesn't have to be a cycle. It's just, so here's U. And it has some edges, going into it. So these 5 edges that I drew, let me just make more, they don't have to correspond to the number of nodes. These edges are all delta of U. That's what those are. And we know that any one of them, so how many of these edges is contained in any particular mi dash? Well, mi dash. Either none or 1. And why is that? Because mi dash is a graph. It is a perfect matching. 1, 2, 3, 4. 1, 2, 3. I redrew all 7 edges here coming into my collapsed. Oops, sorry, I'm making it a little too messy here by arrows that look like edges. My collapsed node. So obviously, any perfect matching can only have one of them. So each matching mi dash and mi double dash contains at most one edge of these, but actually, because it's a perfect matching, it contains exactly one edge, one of those edges. So what does that mean? It means that for any given edge, let me pick a different color. So for any one of these edges, we said that each mi, they're the same number of perfect matchings in the dash set that contain that edge as the number of perfect matchings in the double dash set. So this means that we can pair up all of those matchings. So since each mi contain in each mi dash and each mi double dash contains exactly one of these edges, I can pair them up. So in other words, by renumbering, if necessary, we can pair up mi dash and mi double dash so that for all I, mi dash and mi double dash, we said that each mi dash and each mi double dash contains some edge, one edge of delta of U, and I can renumber them so that they contain the same edge. M1 dash and M1 double dash contains the same edge, M2 and M2, M3 dash and M3 double dash. So that they contain the same edge in delta of U. So why am I doing this? I'm doing this because this is going to allow me to now stitch together the matchings where so I have one matching where I collapsed U, and one matching where I collapsed everything outside of U. And what is common? What is not collapsed? The thing that's not collapsed is the number of the edges that are going from U to not U. Right? Those are the only things that I have to worry about. But, right, because any edge that's inside of U is collapsed in all the mi dashes. So it's just not there. I removed those coordinates. And every edge in that goes from not in U to not in U is collapsed in m double dash. I need to merge those. And now I can merge them because in the overlap they have this perfect agreement. So I encourage you to kind of to just draw this out. So how could we draw X? X has three parts. It has edges from U to U. It has edges from U complement to U complement. And it has edges from U to U complement. Again, the directionality doesn't matter. What is X dash? X dash, I've collapsed U. So I basically take away this part, and X dash is just all of these edges. And what's X double dash? It is, is this notation, let me try again a different way. So X dash, this goes away, and this follows. This is the same as above. And for X double dash, it's this middle component that's deleted. And so these edges follow. And so when I want to merge, if you give me X dash and X double dash that are made up of perfect matchings, I only need to worry about this domain, because everything else, these part of the coefficients and these part of the coefficients are already expressed as this nice convex combination of integral of perfect matchings. So I just need to worry about this. This is the stitching together that happens. And this is what this result is telling us, that we can now stitch it together in this way, and therefore I can define mi as the union of mi dash and mi double dash, and the claim that this mi is a perfect matching. That is the whole point. But if mi is a perfect matching, what this means is that we finished our proof. It means that X, after all, was in the perfect matching polytope because it's equal to 1 over k times the sum of chi mi. And that is our story here. So that finishes this proof. In the next lecture, we're going to use this in order to show that the matching polytope that we wrote down at the beginning of this lecture is indeed equal to QM. So we're going to pick that up next time.